Hello everyone. Have you seen any physics students wearing this kind of t-shirt? And God said, and here's some equation, and then there was light. This is obviously a parody. This phrase was taken from the Bible. In the Bible, they said that God said that there shall be light, and then there was light. That was original phrase in the Bible, and then some physicists changed it to this Maxwell. Actually, this is for Maxwell equations. It's one of the most beautiful equations in the physics to make this kind of t-shirt. And this has a very deep meaning because the Maxwell equations predict there is a light. So that's why it continues to, then there was a light. So today we're going to look at this Maxwell equations. These are one of the most beautiful equations in the physics, and then I hope you understand the reason why it's so beautiful. So today's topics are something like this. So to understand how Maxwell completed the set of four equations that describe all electromagnetic phenomena, to explain the existence of electromagnetic waves and how they can be produced by accelerated charges, to understand and describe the properties of electromagnetic waves, to describe the electromagnetic spectrum, to determine energy and momentum in electromagnetic waves. Let's get started. So far we've learned four equations of electromagnetism. So this is something we already learned. We've seen four fundamental equations. This is a list. Let's look at it one by one. So this is Gauss's law for electronic field. So if you integrate electronic field in a closed surface, then that is equals to the charges inside that surface. So this is Gauss's law, right? And there's a Gauss's law for magnetic field. In terms of magnetic field, if you integrate magnetic field in a closed surface, that equals to 0. Because there's no magnetic charge in this world. There's no monopole for magnetic field. So if you integrate, it becomes 0. So that's why 0. But it's very similar, right? Symmetric, right? Then there's a Faraday's law. Changing magnetic flux produces electric field. So if you change the magnetic flux, that will produce the electronic field. Produce the electronic field. Right? For example, the magnetic field, if you change it, then there's a current in a coil. That's Faraday's law. And the last one is Ampere's law. So if you integrate magnetic field in a closed loop, and then that is equal to the current inside that loop. Or on the other hand, electronic current produces magnetic field. So if you have a wire and there's a current going on, there's a magnetic field around it. That's Ampere's law. But if you remember, if you are careful enough, this I mentioned is only for steady currents. When the current is constant, you can use Ampere's law, but not when current is changing, increasing or decreasing. So this part was incomplete. Okay, then Maxwell thought something like this might be here, because if you change, so this is very symmetric, right? If you integrate E or B, you get Q or 0. So if you change magnetic field, there's a current, right? So maybe if you change electronic field, there may be magnetic field. That's what Maxwell thought about. Then these two will become more symmetric, right? So something like this. So what Maxwell thought about in 1960 is you think about this kind of circuit. See, there's a voltage and a resistance and the current go through and it's an inductor. Then try to apply the Ampere's law to here. So this is a schematic view. And then let's try Ampere's loop here, loop 1 here. And then you integrate magnetic field. Ampere's law says if you integrate magnetic field, then that equals the current inside, right? Then if you integrate 1, that's fine. If you integrate 1, there's a current here. 2 is fine. 2 in this kind of surface, a little bit to the left. If you integrate magnetic field, that equals the current inside. That's fine, right? And then 4, let's look at 4 first. 4 is this big loop. 4 is also fine. If you integrate whole thing, there's a current going on. Current going into the condenser and then going out. So that's fine, right? There's a current going through. So Ampere's law is also true. Integrate magnetic field, then that equals current. But then there will be a problem if you take a surface like 3 in between here. Then if you take this surface, there's no current, right? Because the current doesn't go through in between here. It stops here. So this part is going to be 0. But there is still magnetic field. So what's going on? This is the reason why we didn't use Ampere's law for changing current, because this current is changing, right? As the more and more charges accrues here in C, the current is changing. So we didn't use Ampere's law to changing current. And then Maxwell thought about it. When electronic field is changing, that might induce the magnetic field. So he added this term. Actually, he predicted to make it more simple, and he predicted if you change electronic field, there should be magnetic field. So that's Maxwell's insight. And then later, people, 1980s, I think 1980, 1888. So 1860, Maxwell thought about this idea, and 1888, Hertz, German physicist Henry Hertz did experiment to check this, and then there was this term confirmed in 1888. That's amazing, right? Hertz is the same person in the unit of frequency, Mr. Hertz. Okay. Then let's go next. Okay. Right. Then so this is the term Maxwell added. Now the Maxwell equations for fundamental laws of physics are complete. And these are called Maxwell's equations. 2 Gauss's law and Faraday's laws, Ampere's law. These describe all electromagnetic fields in the universe except the very quantum physics in a very microscopic world. And this is a new term. Electronic current and changing electronic flux produce magnetic field. This term is in vacuum, the Maxwell equation is completely symmetric. In vacuum, there's no electronic charge, and therefore there's no electronic current. Then what happened to Maxwell equations? There's no charge, so this is 0, right? So 2 Gauss's law becomes symmetric. And then also Faraday's law is Faraday's law, and Ampere's law, because there's no charge, there's no charge current. So this I part is also dropped. Then this Ampere's law and Faraday's law are symmetric, right? Changing magnetic field, magnetic flux produces electronic field, changes electronic flux, produces magnetic field. So this is Maxwell equations in vacuum. And the difference from the reality is there are charges in real world. So there's a charge and a current. So there will be Q here and there will be I here. Okay, then what's another deep prediction from Maxwell equations is there will be an electromagnetic wave. Let's look at it. And then that's predict there will be a light. So that's what we then that comes to the t-shirts at the beginning. So playing electromagnetic wave consists of electronic and magnetic fields that vary in space only in the direction of the wave propagation. So imagine this kind of wave. So electronic field is going this way and then B is going together in 90-degree angle going through this way. Okay, the fields are perpendicular to each other and to the direction of propagation, and then mathematically the wave field shown in the figure have the form because this is sine curve. So both electronic field and magnetic field varies with sine curve. Okay, these are synchronized because the same phase, and then they are perpendicular. So it goes this way and B goes this way. Okay. Then let's look at the Maxwell equation in this kind of case. Since the field lines of electromagnetic waves extend to infinity, they have no beginning or endings, and that satisfies both Gauss's law for electricity and Gauss's law for magnetism. So that's okay, right? Then let's try to apply Faraday's law. If you remember, Faraday's law is something like this. If you change the magnetic field flux, then there will be electronic field. Okay. Then let's look at the electronic field in this. Let's look at this figure. Electronic field is parallel to the plane, so electronic field is going this way, right? And then its strength and direction vary towards position x. So if you change x, the strength change, and sometimes this way. Magnetic field is perpendicular to the page, so it's going this way. And again, strength and direction changes sinusoidally with position x. So if you go a different x, magnetic field, electronic field, both change. And then Faraday's law, so you have to integrate magnetic flux. For example, let's take this small loop of the distance in x is dx. Then the electronic field, how much does it change? It's here it's minus EH, say for example, the height of this box is A, then it's EH, right? And if you go a little bit farther, then it changes a little bit dE. So the difference should be H dE in electronic field integrated. Well, what about the change in magnetic flux? Magnetic flux change is H doesn't change, and so it's dB dt. So how much magnetic field changes from here to here? So that's the change. And then these two are the same. These two are the equal. These two, this one and this one, are equal. So that's what Ampere's law says. So this becomes this. E derivative becomes B derivative, with H disappears, right? H is common to both terms, both sides. So we get this, okay? And then let's apply Ampere's law in the xz plane like this. So now this is looking at from the other direction, from y direction. This is z and x. Before it was y and x, now z and x. The electronic field, so now magnetic field is parallel. So this is magnetic field now, because we're looking from different angle. And then strength and direction change with x. The electronic field this time is perpendicular to the page, and like this, and or this, and then changes as a function of x. And let's apply Ampere's law in this small rectangle here. Ampere's law is B integrated is, if you integrate B in a loop, then you get current and then change of electronic flux. Okay. Then what's the change in B? Again, if the length of the box is h, then BH minus B plus dBH. dBH is a little bit of change in the magnetic field here. So you get minus h dB. What is the change in electronic flux? It's again, you move a little bit and you just change dE dt because h doesn't change. And Ampere's law is saying this equals this, so this dB h dropped equals this. Okay, so that's Ampere's law telling us. And then I apply these conditions to sinusoidal plane waves. So the actual form of E and B in this case is sine, right? So let's put sine in. So E by the derivative of x is sine derivative, so it's going to be cosine. B derivative of sine is cosine. Okay. So if you look at these two, this part, cosine part, is the same, right? They are in phase and both cosine. So this part must be equal. So Ke peak value equals omega Bp equals. And then similarly, the Ampere's law, if you put sine, then you get these numbers, and then you get this Kb equals epsilon 0 u0 w omega e. And if you combine these two, then you get velocity equals omega divided by k, or 1 over square root of epsilon 0 u0. And then in another words, so this is wave, right? So Maxwell equations predict there will be electromagnetic waves. So electromagnetic waves satisfies Maxwell equation. So Maxwell equation, one of the predictions of Maxwell equation is there will be electromagnetic waves. And this is a new phenomenon at that time was not known to people. And then what's the speed of this electromagnetic waves? We can calculate, right? The speed, velocity of this wave is this, and we already know the value of epsilon 0 and mu 0. So why don't we put these numbers in? And then what happens? This is permeability constant for magnetic field. Epsilon 0 is permittivity constant for electronic field. So we put this in. And then what happens is we put this number. We have seen these numbers several times previously. And you get this. 3 times 10 to the 8 meter per second. Are you familiar with this number? Yes, this is the speed of the light. Precisely the speed of the light. So this is telling us the light we see, so this projector is using the light, right? This light we see every day is electromagnetic wave described by the Maxwell equation. That's interesting, isn't it? Then, as previously shown, the amplitudes of E and B are related. in this kind of relation because this is this. So the ratio of EB peak value is ratio of omega divided by k. That is speed of the light. So any wave amplitude is possible as long as you satisfy this equation. So E is larger, B is larger, or B is smaller, E is smaller. And also any frequency or wavelength is also possible as long as this omega divided by k equals c. Or equivalently, f lambda equals c. So in high frequency case, high frequency, omega is smaller, k is smaller, you need to satisfy these equations. But any frequency or wavelength is possible. That's why there are light with different wavelengths, long wavelengths, short wavelengths, X-ray, radio. These are all electromagnetic waves. Let's look at the polarization. The electric and magnetic fields of electromagnetic wave in a vacuum are perpendicular to each other and to the direction of propagation. But any orientation in the plane perpendicular to the propagation direction is allowed. The direction of the electric field defines the direction of wave's polarization. So electromagnetic waves, in this case this gray line, are polarized in the direction of their electronic field. Here the polarization is vertical, y direction, in the y direction, right? So E is changing in y direction. So that, in that case, we say the wave is polarized to the E's direction, y direction. In this case, polarization is horizontal because electromagnetic E is changed in a z direction. So this is G polarization. Okay. And then Morse law. Typical light sources emit a mix of waves of random orientation. Such light is said to be unpolarized. Unpolarized light can be polarized by reflection or by passing it through a polarizer. So typical light, the E direction is random, then it's unpolarized. A polarizing material such as polarized has a preferred direction known as its transmission axis. Only the component of the electric field parallel to the transmission axis passes through the polarizer, namely E cosine theta, where theta is the angle between the transmission axis and the electric field. A wave of intensity S0 emerges from polarizer with intensity. So if you want to calculate intensity, no intensity of the light coming from polarizer, you can use Morse law, and actually it's S equal S0 cosine square theta. Okay. And then one of the very common application of this polarization is LCD, liquid crystal displays. LCDs, we use it in computers or cell phones, right? This is using liquid crystal to rotate the polarization of light, either blocking the light or allowing it to pass. Many individual pixels make up a typical liquid crystal display. So, in one pixel of our LCD display, it is like this. So, this is a white light. Electric field of incident light points in all directions perpendicular to light's propagation. So it comes through. It's a random direction. But vertical polarizer passes only light with its electric field vertical. So through this polarizer, only light polarized this way can pass through. Then liquid crystal, there's a liquid crystal. The molecules align with striated plates and loaded light polarization. So this liquid crystal rotates the light. And the horizontal polarizer passes the now horizontally polarized light. And then the light goes through. And then applying the voltage aligns the liquid crystals. So you can change the voltage here to change the direction of liquid crystal, so you can control what kind of light are coming out. they no longer rotate the light's polarization. Horizontal polarization now blocks the still vertically polarized light. So in this way, you can adjust the light amount of the light coming out. For example, you can increase the blue light more, reduce the red light more, reduce the red light, then you can create a blue image. If you increase the green light more and suppress blue and red light, then you can produce green image. That's why you can show different images on the display. That's how LCD display works, using the technique of polarization. Electromagnetic spectrum. So as I said, any frequency or wavelength is possible for EM waves as long as you satisfy F lambda equals C, this relation allowed from Maxwell equations. So that's why electromagnetic waves come in a vast range of frequencies and wavelengths, from low frequency radio, long wavelength radio waves, through very high frequency X-ray or short wavelength gamma rays. Visible light occupies the wavelength ranges from 400 nanometer to 700 nanometer. So visible light to our eyes are only very small part of the electromagnetic spectrum, only 400 nanometer to 700 nanometer. And in a shorter wavelength than that, you have ultraviolet light, we cannot see it, but X-ray is X-ray, gamma rays, very short wavelengths. In longer wavelengths, there's infrared light, we cannot see it, but it's light. Microwave, cosmic microwave, background is microwave, and also radio waves, very long wavelengths. See, these are like a kilometer scale wavelengths. Producing electromagnetic waves through different physics. Electromagnetic waves are generated by accelerated electronic charge. Details of emitting systems depends on wavelengths, with most efficient emitters being roughly a wavelength size. So that's why radio waves are generated by alternating currents in metal antenna. So they say this is metal antenna, and if you change the current, then EM waves is going to be emitted. So this is radio transmitter and also antenna. If you receive the EM wave, the current changes in a wire, and then we receive it. And then because the EM radio waves of wavelength is long, we need a big antenna, visible antenna. Molecular vibration and rotation produce infrared waves. Visible light arises largely from atomic scale processes. For example, for infrared, our body, our temperature is something like 36 Celsius, right? Nowadays, we measure every day. This produces infrared light. So that's why, for example, if you go to airport, they have infrared camera to check your body temperature. If you have high temperature, you emit more higher and shorter wavelengths infrared. If your temperature is normal, you get lower intensity, lower temperature infrared. X-rays are produced in a rapid acceleration of electronic charges. Gamma ray results from nuclear processes, because that's very small region, right? Okay. Then what about energy in EM waves? EM waves carry energy of their electronic and magnetic field. So, if you remember, energy of electronic field is 1/2 epsilon E squared, right? And magnetic field is similar. Energy in magnetic field is B squared divided by 2 mu 0. So energy, you just sum it. So the total energy of EM wave is the summation of these two. Summed energy in electronic field and then magnetic field. So this is the energy in an electromagnetic field. If you wanted energy to be per unit area, you drop this A is the area of the wave, so unit area. Then you get this pointing vector this is the rate of energy flow per unit area. So that's energy. Okay. Then I use E equals CB to change this to this, and this is the shape of the Poynting vector. And then if you want to know average intensity, then this is sinusoidal curve, right? So you just divided the peak energy by square root of 2 square root of 2, so that's 2. Then this is the average intensity. Again, intensity of waves from a local source drops off as the inverse square law of the distance from the source as the wave's energy spreads over the spheres, right? Large areas. So you just divide S equal energy divided by R square. So that's the surface of the square. Where B is the total power emitted. This is the same as light intensity. Then, if there's energy, there's also momentum too. Electromagnetic EM waves also carry momentum. The wave energy is U, then momentum P are divided. You can get it by dividing by C, because the velocity is the speed of light. So U divided by C gives you the momentum. So that means these EM waves have a radiation pressure. So if there's a light, then there should be a pressure, momentum. Of course, this value is usually very small because C is very large number. So if you divide it by C, the radiation pressure is very small, but you still have the radiation pressure from light. And there are some people trying to use, for example, use this radiation pressure for the spacecraft. If you launch a spacecraft in space, then you need some energy to push it forward, right? But carrying a lot of fuel is expensive and it's going to be heavy. But for some time, in a space, there's a sun. The sun is always emitting strong light. So you open a solar sail in space and then receive this radiation pressure from the sunlight, and they use it to propel the spacecraft. This kind of spacecraft are being planned and maybe possible in the future. Okay, so here's a summary of what we learned today. Maxwell equations describe all electromagnetic fields outside the realm of the quantum physics. So these are Maxwell equations. They include Maxwell's modifications on Ampere's law to show a changing current electronic field produces a magnetic field. So Maxwell's insight is he predicted this term, changing electronic field produce magnetic field. And the now equations are complete. And this equation show that EM waves are possible. That's the light. And then in the vacuum, the speed of the wave is exactly the speed of the light, 3 times 10 to the 8. And then we learned this relation, E equals CB. Electronic magnetic fields are perpendicular to each other, and to the direction of propagation is also perpendicular. Frequency and wavelength should follow F lambda equals C. The range of frequency wavelengths comprises the electromagnetic spectrum, from radio wave to optical, UV, X-ray, gamma ray. There's a variety of wavelengths and frequency. EM waves ultimately originate in accelerated charge. EM waves carry both energy and momentum. Okay, so that's we learned today about the Maxwell equations, and then that's predicted light. That's amazingly beautiful equations, I believe, in physics. Okay, I hope you enjoyed the lecture. See you next time. Bye-bye.